Okay, it's now 8 a.m. GMT. Let me start. Hello, everyone. Good afternoon here in Indonesia, in Australia, in China. Welcome to 16th session of the ISRM Young Members Seminar Series. My name is Yudhidya Wicaksana from Institut Teknologi Bandung, Indonesia. And I'm here, pleased to be here today alongside my fellow ISRM Young Members Coordinator, Dr. Babak Khadifi from AMC Consultants Australia and Dr. Dan Lee from Curtin University, Australia. Thank you all for joining us today. It is truly a pleasure to host this session and to have such an engaged audience from around the world. Before we begin, we would like to extend our sincere gratitude to the ISRM, International Society for Rock Mechanics and Rock Engineering, especially to the ISRM Young Member Committee for their continued support of this initiative. To the youth representative of National Group who have actively contributed to make this series success. And of course, our speaker for today, Dr. Yingchun Lee, Mr. Fauzan Yudho Pratomo, and Dr. Yuqi Song for agreeing to share their research and insight with us. Okay, let me talk a little bit about this seminar series. This seminar series is dedicated to fostering the strong young community in rock mechanics, bringing together engineers, researchers, students to exchange knowledge, sharing experience, and build international connection. We encourage young professionals to participate as speakers. Yeah, all of you can be speakers here as long as follow these rules. The nominees should be first an ISRM member, and the second be under 35 years old or under 40 if they obtain a PhD within the past 5 years, and also have no more than 10 years experience in rock mechanics and rock engineering. So the nomination can be submitted to the by national group, by colleagues, by organization, or even as self-nomination if you are confident enough to email us. And then if you're interested, you can find the contact detail here on the screen. And then we would love to hear from you. All right, then for today's seminar session, each presentation will last 20 minutes, followed by 10 minutes Q&A session. And then to ensure a smooth experience, we kindly ask everyone in the audience to keep the cameras and microphone off during the presentation. You may turn on again after in the Q&A session later on. Use the chat or raise hand feature to ask questions. All right, let's now begin. It is my pleasure to introduce my friend, today's moderator, Dr. Dan Lee. Are you here, Lee? Dan? Dr. Lee, are you here?
Yes, I'm here.
Yes, all right. Okay. Dr. Lee is a senior lecturer in the Western Australian School of Mines, Curtin University, where he has been since 2021. He previously served as an assistant lecturer at Monash University from 2019 to 2021. His PhD in rock mechanics with focus on ground support was completed at the University of New South Wales in 2019. Since 2023, he has been an active member of the ISRM Young Members Committee. Okay, I will hand over the remote control to Dr. Lee. Dr. Lee, the stage is yours.
Okay, thank you, Yudi, for your kind introductions, and thank you, everyone. As Yudi introduced, my name is Dan Lee. I'm currently working at Western Australia School of Mines at Curtin University in Australia. And today, I would like to first thank all the three speakers for giving their valuable time to this seminar. And I would also like to thank all the audience to give your time to participate in this research seminar. And hopefully, all the audience will get something out from here after today's workshop. So now let's start with the first presentation and by our first speaker, Dr. Yingchun Li, and Dr. Li is I'll say is an old friend of mine, and he did his PhD in rock mechanics, particularly with the focus on the rock joint shear at the School of Mines at the University of New South Wales, where we met each other. And proud to University of New South Wales, Dr. Li did his bachelor degrees at School of Mines at China University of Mining and Technology, which is the top one school of mines in China. Right, and since he finished his degree, his PhD degrees, he joined the Department of Civil Engineering at Dalian University of Technology in 2017, where he studied his faculty position and academic career. Right, he has built up a very strong track record a lot since he joined Dalian University of Technology, which can be evidenced by his publications. So far, he published over 90 articles. Right, today, Dr. Li will give us a presentation on the peak shear strength of rough rock joints via normal deformability test. Right, so now let's welcome Dr. Li. And Dr. Li, the time is yours, and please go ahead.
Thank you, Dr. Dan Chi. Is it clear?
Yeah, it's all good.
Okay, so good morning, afternoon, and evening, ladies and gentlemen around the world. Thanks ISRM, thanks the Young Committee, thanks all the staff, and thanks Dan Chi for inviting me to this seminar. Thanks all the attendees. This is Yingchun Li from Department of Civil Engineering, Dalian University of Technology, China. And today, I will talk on how to predict the peak shear strength of rough rock joints while the joint normal deformability. As we all know, due to the long geological processes, rock masses contain various types of discontinuities, such as joints, fracture, and faults. These discontinuities or joints are inherently rough in multi-scales, from micro under the microscope to millimeter scales in the laboratory to meter scale in the field, and also kilometer scale along the global plates. As has been pointed out quite a long time ago by the ISRM Commission in 1979 and 78, quantitative description of the nature of discontinuities has long been a burning issue in the field of rock mechanics, focusing on how the discontinuities or joints are deformed, among which the shear or the slip behavior is crucial to understand the deformation and failure of rock masses, such as rock slope sliding, and underground wedge collapse. Besides the practical significance in rock mechanics, the shear behavior of rock joints has more wide implications spanning geophysics, such as the faulting and precursors to shallow earthquakes, and solid mechanics, such as interfacial slip and friction between solid contacts. Assignment. I all have this. Sorry.
Losing him?
Yes. Okay, sorry. Yes, I'll try to hide the panel. Yes, all good now, right? All good?
Yes, all good. All good, all good.
No good?
Yes, all good. Please go ahead.
All good? Good or not?
It's all good. It's all good. Dr. Li, please go ahead.
Okay. So in the field of that I'm working on is for the rock mechanics or geotechnical design, we care the most the peak shear strength of natural rock joints. In the past decades, dozens of shear strength criteria have been available in the literature, and they can be classified into three groups. The first is aspirated slope. I0 based models. The second, the GRC based models proposed by the very famous scholar Dr. Barton, and the 3D asperities slope theta based model proposed by Professor Grassley in University of Toronto. However, most of the reported models have several key limitations, including lacking sound theoretical foundation, unclear mechanical contributions by the roughness, and also they cannot consider the contact states after deformation, and with limited predictive capability to the field applications. Thus, in the following, I will report a new peak shear strength criterion that overcomes the above shortcomings. Let's consider the shear process of a rough rock joint. Under a low normal confinement, the asperity will climb over each other and yield dilation. When the normal stress gets higher, the asperities will be partially or fully sheared off, depending on the magnitude of the normal stress. Thus, it's clear that to predict the shear resistance, we need to quantify first the peak dilation angle and also the shear off portion. The partitioning of the dilation and the shear off can be represented by the shear off ratio. The shear off induced component is a function of the shear off ratio and the constant asperity strength, which involves the basic friction angle and the transitional normal stress. The proposed theoretical framework, it strictly satisfies the physical constraints of rough rock joint subject to different magnitudes of shearing. From the mechanical viewpoint, when the normal stress is nearly zero, no asperity damage, and thus the total friction angle is the highest. And as the normal stress grows to the transitional normal stress, a very high normal stress level, the total friction angle decreases continuously to the basic or the residual friction angle, which is a constant. During this normal stress change, the dilation angle declines from the maximum at the initial asperity angle to 0, and the shear off ratio grows accordingly from 0 to 1. Thus, the key to predict the peak dilation angle is quantify the contact states after loading, normal loading, but before shear, since when we are doing direct shear test or considering the rock joint in the field, they are confined by normal stress. Since the contact states of the rock joints are changing over the normal loading, we treat the real contact area growth process as a consequence of the joint aperture reduction from 0 normal stress to the prescribed value, and we assume that the joint aperture follows the classic normal distribution. Then after mathematical derivation, we can predict the real contact area ratio as the error function of the joint closure and mean aperture. Then if we have the joint closure curve from the fundamental normal deformation test, the real contact area ratio over compression is determinable. To validate the formulation to predict the real contact area ratio, we compared our theoretical predictions to experimental measurements conducted by our co-author who used the pressure-sensitive film to image the contact zone and associated area on the compressive normal loading. From the correlations, we can see that our theoretical work achieved very high accuracy. For details, the audience can refer to the publications in 2023. After the real contact area ratio is determined, we can predict the peak dilation angle by considering the relationship between the real contact area and the angular distribution of the roughness along the surface. We derived the peak dilation angle is a nonlinear function of the CDF of the aperture and the 3D morphological parameters denoted by theta star and C. When the peak dilation angle is determined, we can locate the asperities that are truly sheared by comparing the slope of each asperity to the peak dilation angle. The asperity with a higher slope than the peak dilation angle is truly sheared, and otherwise it will not be involved in shear and will not counted in our model. If we have a close look at the equation for predicting the peak dilation angle, we found it also strictly following the physical constraints. That is, when the normal stress is nearly 0 or very low, the CDF of the joint closure is 0, normalized value, and the peak dilation angle is the maximum. And when the normal stress is as high to the transitional normal stress, the CDF of the joint closure is 1, meaning fully contact and the peak dilation angle decreases to 0. Once the peak dilation angle and the truly sheared asperities are determined, we can compute the shear off ratio. That is the ratio between the shear off area of each asperity and the initial asperity area facing the shear direction. We found that the shear off ratio is only related with the geometrical properties, including the asperity slope, amplitude, and the wavelength, and the peak dilation angle. The geometrical properties can be easily measured by the 3D surface digitization and the reconstruction technology. And the final slope to predict the peak dilation angle is to get the transition normal stress of different of the joints on the different contact states. This contact states includes both the initial contact state before normal loading and the contact state after normal loading prior to shear. It means that if the roll joint is initially unmatted, it's good, and also if it's initially unmatted and then after compression is matted, is also effective. And previously, we already proposed a nonlinear equation to predict the transitional normal stress as a function of the initial asperity slope and rock strength, but only for the fully closed roll joints. By considering the real contact area of the joint walls of different contact sets, here we show an improved equation where the initial asperity slope is replaced by the initial slope of the truly sheared asperities. Since on the different contact sets, the asperities truly sheared are different. To determine the initial slope of the truly sheared asperities, we use the concept of the weighted average dip angle that quantifies the relative contribution or density of the asperities with dip angles higher than the peak dilation angle. Then the derived equations of the initial dip angle of the true sheared asperities can be predicted by the 3D morphological parameters and the real contact area ratio. When the normal stress is 0, this initial asperity angle is the maximum. And when the normal stress arrived at the transition normal stress, this angle is the average value of all the asperities. Now we have determined the peak dilation angle, the shear off ratio, and the transitional normal stress. And thus, the peak shear strength can be predicted. To implement, what we need is some very fundamental rock mechanics test, including first, to acquire the uniaxial compressed strength of the rock matrix. And second, the joint morphology information, via 3D digitization, and the basic friction angle of the joint of the rock joint. This value, first, it can be measured by a direct shear test on flat rock joints, or it can be estimated or roughly determined from the literature, since there are extensive data on the basic friction angle. And very quick, normal deformation test on the rock joints. If this test is unavailable, we can also adopt very classic prediction models on the normal deformability, such as the Goodman model, the Barton-Bendis model, and the log model. To validate the proposed peak shear strength criterion, we conducted in-house experiments, including both the normal deformation test and the direct shear test on various types of roll joints using our direct shear test machine in our laboratory, containing both natural rock joints, namely the red sandstone joints, the diabase joint, and artificially made rock joints, synthetic joints made of gravity. And we applied low to high normal stresses to obtain a very diverse range of the peak shear strength. During this process, since we are doing controlled laboratory test, we measured all the parameters required by our model very accurately. And in computing the 3D morphological parameters, we found a very interesting phenomena that is, if we do direct fitting the asperity angle distribution using the graphics approach, it usually yields a very biased assessment of the true sheared asperities, since it includes very high angular asperity. Sometimes its value can reach more than 80 or 85 degrees. This is this doesn't make any sense. But these asperities are few, and also these asperities we found are very few and very tiny. From a mechanical aspect, it provides very minor shear resistance and shall be excluded from the fitting. Thus, we optimize this fitting process by trial and error to achieve the best performance. We compared our analytical predictions to the experimental measurements and found that our predictions yielded satisfactory results with the absolute error within 2 megapascal and the relative error no more than 12%. Since we also compared the prediction performance of our model to a branch of existing models, including the classic, the very widely used buttons GRC-GCS model, the SEBIS model, Gracili's model, and the model I proposed earlier, which is a very simple prediction of the peak dilation angle. The comparison shows that overall the established model reached 5% to 20% enhancement of the prediction accuracy. It seems that it's only not that much improvement, but our model is fully predictive. And some of the models are listed here requires co-fitting or additional direct shear test. So to summary, first we proposed a new peak shear strength criteria for 3D rough rock joints. And second, in the model considered the true shear asperities and quantified individual dilation and shear of behavior contributed by the roughness. Third, the model is predictive with basic morphological analysis and rock mechanics test. Also, the model is preparedly to embrace rock joints of different scales, giving joint surface data on the normal deformability relationship. Since our model only requires the morphological parameters and the normal deformability of the rock joints. So in the near future, first, we will provide a model incorporating the scale dependence. Second, we are working on a standard procedure to optimize the 3D morphology parameters. Since we found that the procedure that we used to optimize the morphology parameters are quite empirical, and now we are trying to provide a very strict and scientifically reasonable approach to do the 3D morphology optimization. Also, we are trying to extend the model to more complex engineering and geological settings, including different shear rate and fittings, and also the effect of geofluids. Last, we are trying to implement our model into the DM code for field scale practice, since our final approach in rock mechanics or geotechnical analysis is to do stability analysis for rock slope and all underground excavation projects. Okay, this is my talk. Thanks for your attention. So question time.
Okay. Thank you, Dr. Lee, for your excellent presentation and in-depth research into the predictive model of the peak joint shear. And I can see it's a very math intensive, and I hope the audience have been following well. So, and we know like a peak joint shear has been very important strength parameters for rock engineering, right? As it can be an input to the numerical simulations. So doing some research related to this area is quite useful and meaningful for the engineering applications. And it's good to know, like after those pioneer works, we still have some young scholars still doing this research, trying to increase the accuracy, so compared with the previous models. All right, so now I think the floor is open to the audience and for any questions. So does anyone have any questions?
Yeah, hi, Dr. Lee. Yeah, Associate Professor Lee. Yeah. So thanks for your presentation. So I really enjoyed it. And I'm doing similar research using DEM. So as you mentioned in your future research, you will use the DEM. Yes. So I know that the roughness of the rock is it's an important parameter to influence the peak load. Yes, and DEM is a good method to investigate it. Yeah, so I'm also very interested in the roughness, so the roughness on the influence of roughness on the peak load. So can you talk a bit more about how do you consider roughness in your model, in your constitutive model on the peak load? Yeah.
Okay, so Dr. Song, right? So thank you for your comments. Yes, we are I'm with my students are working trying to incorporate our proposed the constraint model in DM. What the DM I'm using is UDEC and 3DEC. Since in UDEC and 3DEC, there are connections or in fact connections through fish language or C++ language to write a package, and using the package, the UDEC code can the UDEC code can dictate the package and then do stress displacement analysis automatically. So this is what we are doing now. So it's not like PFC. Since in PFC there are particles. In unit particles, we need to do. My understanding that particles is deal with more the contact problem, the microscopic contact using the Hertz contact and the Medellin contact. What I'm working with UDEC, since they directly employ the constraint model, so I will so they can be incorporated readily using unit language to directly write a package, write a constitutive model, the package. This is what we are doing now.
Yeah, thanks for your answer. Yeah, so I'm using PFC to do the roughness, to investigate the roughness of the rock and the rough fracture, but not a smooth fracture, because usually the previous research they insert a smooth fracture into the model, and actually in natural. In natural scenario, the fractures are seldom smooth, but usually it's roughness. So we consider roughness in the PFC. Yeah. And I think 3DEC is a good choice because it can catch the microscopic and catch the fractures, the failure. Yes, the rock failure. Well, yeah. Thanks.
Yes, the difference between between UDEC and PFC is that FLAC is only it's not easy to build the roughness, explicitly. I mean, build the geometry. It's not easy in DM, that in UDEC. So we use the constitutive models. And in PFC, if the fracture is rough, you can build a rough geometry. And in this case, we focus more on the contact between the particles.
Yeah.
Right.
Yeah. Right.
That's the difference.
Yeah, we can talk more about this topic in the future. Yes, I will follow up your work. Yeah.
Okay.
Thanks.
Okay.
Very
Thank you.
interesting.
Okay. Thank you.
Thank you, Dr. Song, for your questions. Anyone else have any questions for Dr. Lee? We still have a few more minutes left for Dr. Lee's session. Anyone else? Okay, so all right. So if nobody else has any question, I have one small questions to Dr. Lee. So you were saying one of the advantages of your model is able to capture the field scale peak shear strength. right? Barton also proposed some, right, with some modification of GCS and the GRC. And so my understanding is the way how you can capture the peak shear strength at the larger scale is relying on the information, the morphological information. Is that right?
Yes, exactly.
So how do you get this morphological informations?
Yeah, very good question. What we can do first. Sorry. What we can do first,
give me
if
one second,
if the row joint is exposed, I mean we can see, or if we can accessible to the larger scale row joints, we can directly digitize while scanning, while the larger scale scanning. If we cannot accessible to the row joint or only with limited information, we can try to extrapolate to the larger scale roughness from some statistic analysis, like the DFN or like the stochastic process model. There are a branch of these models. So yeah, so with this data, with the assured or determinable the joint surface, we can obtain the 3D morphological parameters and then introduced to our peak shear strength model.
Okay, yeah, because in the field, when we're doing mapping the area, the rock joints area exposed to the outside is very limited. It's very limited. So it's probably in the open pit, in surface operations, any surface rock excavations, the area might be big, but in underground it's quite limited. So you cannot get extract all the necessary information, very good information. So of course, like I agree with you, like you mentioned the stochastic, right? Stochastic algorithm to map out the large areas, right? Large area of the rock joints. So that's that might be but the accuracy is, on the other hand, is something like we have to consider.
Yes, exactly. Yes.
Okay, so I saw one gentleman put his hands up. Oh, it's by mistake. Anyone else have any questions? Okay, so if nobody else have any questions, I think that's everything for Dr. Lee's sessions, and I'd like to thank Dr. Lee again, for your time and very insightful opinions in the peak shear strength of the rock joint. And now I think let's move on to the second speaker, right? The Dr. to be Fauzan. And Dr. Fauzan is currently a PhD candidate, right? And at the University of Adelaide, I guess he's working with Murat on the ARC project, and he's working on the multi-scale class 2 fracture behaviors of brittle rocks and rock masses for cave mining operations. And prior to University of Adelaide, Fauzan used to study his master by research in Monash universities on rock mechanics related topics. I guess you must be working with either Professor Ranges or Professor Jian or Professor QB. And because I used to work in Monash, so for 2 years, so I know that those people are normally the people who would go for the rock mechanics research, right? So now and today, Mr. Fauzan will give us a presentation on micro and macro scale class 2 fracture behaviors of brittle rocks in well-controlled Brazilian tests, right? So now let's welcome Fauzan, and now the time is yours. Fauzan, please go ahead.
Thank you, Dr. Dankili. Let me share my screen. So I assume you can see my screen. Yeah.
Yeah, it's all
So,
clear. Voice is good.
Yep.
Voice and the screen is all clear. So please go ahead.
So thank you, Dr. Dankeli, for the introduction. So first of all, not yet doctor, but hopefully soon. So first of all, I would like to say good evening from Adelaide to the online audience, especially to the committee. Thank you for organizing this event. So my name is Fauzan Yudho Pratomo, and I'm a PhD candidate from the Mining and Petroleum Engineering at the University of Adelaide in Australia. So today I'll be presenting an overview of my research titled the Micro and Macro Scale Class 2 Behavior, Fracture Behavior of Brittle Rocks in Well-Controlled Brazilian Tests. My supervisors are Associate Professors Murat Karakus, Jiang Nguyen, and Professor Habui from Monash University as well. This will be the brief outline of my presentation. And I want to start off first with the fact that major surface mines are currently approaching their pit limit, and therefore the transition towards the underground mining is key for the future of the industry. However, there is a lot of uncertainties of rock mass strength and fracture behavior in underground mining compared to the well-established method of the surface mining. Here, Ferguson summarized a list of potential issues to be faced by current and future cave mines, which can be encountered at any stages of the mine during the establishment, the propagation, breakthrough, and even the steady state production. These are summarized as seismicity, high stress, rock burst, dilution, mud rush, air blast, but also complex rock mass conditions, which leads to the unpredictability of caveability and fragmentation. And by with better understanding of the rock mass response and fracture behavior, these issues can be managed better. For example, as I said, one of the significant ones, the caveability and fragmentation, which is related to the fracturing behavior of these rocks. So when talking about the fracture and strength evaluation studies, it has been conducted at multiple scales, from rock mass scale down to the micro scale. However, there are very limited attempts to link these scales, which brings me to the main idea of a bottom-up approach, which is establishing the multi-scale rock mass fracture behavior, or in other words, the characterization of rock mass fracture behavior and prediction of the mechanical response from the micro and macro scale behavior. So first, I would like to talk about OSBIT and the class 2 behavior. So the key term here is class 2 response, where rocks exhibit strain reversal. So they undergo self-sustaining failure from its stored strain energy. Or this is also called the snapback response. So it is clearly different to class 1, where additional work must be added into the system to fail the rock. Existing research suggests that the class 1 or class 2 behavior can only be identified during the test. For example, here in the 20th century, class 2 is often associated with high strength and high stiffness rocks. But after ISRM published the suggested method in 1999, with the use of techniques such as the circumferential extensometer kit, even low strength rocks, they can exhibit class 2 behavior due to these kinds of strain control. So for this first part of my research, I'll be using two rock types, two Australian rock types, which are the Gosford sandstone and the Kalka granite. And by plotting them into the UCS and Young's modulus plots, they somehow show potential class 2 behavior. But still, nevertheless, all these class 2 studies, existing ones, they were for compression tests, and class 2 behavior under tension is rarely discussed. And this is crucial considering that when we talk about rock mass fracturing, it involves complex stress regimes involving both tensile and compression or shear fracturing, especially in caving mechanisms. So from sieve analysis after the UCS test, we can see that how much the granite, this one, is more fragmented, which is a strong indication of class 2 based on past research. And this was a product of the violent bursting failure. The sandstone here, brittle failure, but not too violent. It consists of fine quartz as the main composition, while the granite was dominantly large quartz and feldspar grains. So as shown here in the conventional Brazilian test, the brittle failure will occur as shown here, and without the ability to obtain the post-peak behavior. So in order to get this post-peak response, OSBIT was used, which was developed a few years back within our research group. It started off as the Adelaide University snapback indirect tensile test, now been renamed as the Advanced Universal Snapback Indirect Tensile Test. So in OSBIT, the lateral deformation here, measured by an LVDT that is placed across the diameter, is used as feedback for the loading machine. So we input a lateral displacement rate, which will be maintained throughout the test by a loading machine, instead of the axial displacement or load control in the conventional test. DIC, the use of digital image correlation, and also acoustic emission recordings was also used to obtain more insights into the fracture behavior. As I mentioned, here is the LVDT held in place. So using 3D printed holders and glued on the sides of the specimen. So the gauge will be expanding across the specimen and will measure the diametrical extension of the specimen directly. So the class 2 response here was successfully obtained. So this is after almost 6 hours of testing for the granite and 8 hours for the sandstone. So we can see that over time, this is the lateral displacement. We're controlling it, we're maintaining a predefined rate, and then we're constantly achieving that rate throughout the failure process, which leads to the controlled failure, and we're obtaining this snapback response. So if we look closer at what happened here, so for example, this is a 10-second time frame, because this is 10 seconds out of a 6 or 8 hour test. It shows the gradual process of removing all this excess energy shown by, so these arrows are the movements of the loading patterns. So they are highly sensitive, ensuring a gradual, continuous process of energy dissipation to ensure that this lateral rate is maintained. So as you can see, this is the conventional one for sandstone and for granite. And for the OSBIT one, we're controlling this brittle failure and eliminating the violent nature of the failure. You can see a well-controlled crack is forming. So this is based on the DIC recording. And if we further take DIC strain profiles along the axial vertical axis, it was found, and then we extract these lines into points, and then we observe the horizontal strains along each point. We can see that the lateral displacement is in OSBIT here. It was 12 times the lateral displacement during failure of the Brazilian test. And in granite, it was up to 10 to 30 times the lateral displacement. So it means by controlling this behavior, controlling these Brazilian tests, we're allowing significant lateral extension before the failing. So while from acoustic emission, as shown here, so the majority of the strain energy accumulated in Brazilian tests, they were all released instantaneously during the failure. But by using OSBIT, the hits and then the cumulative energy, it's released more gradually over time. And the B values here also show that the OSBIT has a smaller number of large magnitude AE cracks. And another way to see this is the energy during failure. It was divided by the number of hits. So it becomes a parameter that describes the amount of energy released by each crack. So in sandstone, for each OSBIT crack, it only releases 13% the energy released in a conventional Brazilian test. And for granite, it's only 15%, while in the conventional Brazilian, it releases a significant amount of energy. So this means that OSBIT produced a higher number of micro cracks, while each crack released less energy due to the controlled fracturing. So finally, the scanning electron microscope, or SEM, it was performed to obtain a microscale perspective of the fracture surfaces. So along these fracture surfaces, we analyze the contour of that using the SEM. So first, for sandstone, between Brazilian and OSBIT at 5,000 times magnification, there was no major differences between the two tests. They're both intergranular cracks dominantly being identified. While for granite, the inclined fracture surfaces shown here in Osbit, it shows that the Osbit specimen produced more uniform, intense fracturing, smaller widths between microcracks, which is linear to the high volume of the acoustic hits. And as we see in the Brazilian test, we have quite some amount of debris. So that indicates the components of shear failure and not purely failing in tensile. So in general, there is a strong link between the DIC, the acoustics, and the SEM. And more details about this part of the research can be found in our papers published last year. One in the ISRM and one presented at Europe back in Spain in July 2024. So moving on to some current or ongoing works, we further investigate the size effect. So the size effect was investigated for the granite because of more significant findings compared to the sandstone. So the size effect itself for class 2 response, either in compression or in tension, has not been investigated in detail. So possibly due to possible requirements. So first of all, the circumferential extensometer by ISRM, were usually for specimens less than 100 millimeters in diameter. And the second is the requirement of a highly sensitive servo-controlled loading system. And finally, the requirement of a very large loading capacity. So if we're dealing with large specimens for hard rocks, then we need a machine that could facilitate the need of those large loads. And to get the combination of a highly sensitive servo loading as well as a large loading capacity can be very expensive. So, but if we observe this class 2 under tension, which would be much less than the compressive strength, we might not need a very large load capacity machines. So here for the granite, we investigated 31, 54, and 106.5 diameter specimens. These are the load displacement graph. The post-peak response or the snapback is somewhat similar between the sizes, which suggests that the class 2 behavior is size independent or is actually an intrinsic material behavior. So here the further DIC contours are shown, and since the maximum grain size of the granite is around 5.5 of the largest quartz size, this brings up the ratio of the diameter to grain size around 5 to 6, 10, and 20. And straightforward, simple size effect, there's an evidence strength size effect. And the Osbit strengths are lower, which is expected because of the lower strain rate. And the acoustic energy for each hit were similar somehow in the large sizes for both in Brazilian and Osbit, which suggests there is a possible size limitation of lateral control. So more detailed analysis is to evaluate the crack mechanisms and identify which of my cracks are tensile and which are shear cracks based on the ratio of the average frequency and then the rise angle. So each point here resembles a single acoustic hit. Two values are used based on the latest relevant research to distinguish the tensile and shear cracks based on this ratio. So one clear finding here is that in all the sizes, Osbit has a smaller number of shear cracks compared to Brazilian, which could indicate more accurate tensile behavior compared to the conventional Brazilian test. And the percentages of shear cracks tend to decrease with size in Osbit, and then the opposite in the Brazilian test. While this also interestingly validates the finding of debris in the SEM in our previous part of Brazilian test as one indicator of shear cracks happening, because we know that in the Brazilian, we have a larger amount of shear cracks. So another way to analyze is using a moving average. So a moving average of 50 AE hits was used. So each window here represents a window of 50 hits. This is the data for 54 millimeter or the medium-sized Brazilians. So shear cracks were concentrated when the failure happens. And although the shear cracks seem insignificant in the previous slide, so only around 6 to 8%, it can be seen that in the onset of failure, up to 40% of the shear cracks were involved in the failure in Brazilian tests. But when we're comparing to Osbit, we can see that there's barely shear cracks involved. Although there's some sudden spikes, the values don't mean it's not that significant compared to the Brazilian one. and clearly less number of shear cracks. And in the bottom example, you can notice a quiet phase during the post-peak regime. So the number of hits here during 2 hours, because the number of hits between each interval will be the same, between 2 hours was almost the same of the number of hits during 1 second in the intense fracturing at the end of the test. So here, this was for 31 millimeter specimens. Likewise, similar behavior in the Brazilian test, a lot of shear cracks. And in OSBIT, despite a relatively higher percentage of shear cracks, but still much less compared to the Brazilian test. And this might be due to the low diameter to grain size ratio of this size of specimen. This is for the large one, the large diameter, the 106.5 mil Brazilian one. So relatively higher percentages compared to the smaller sizes. Well, this is under OSBIT, so indicating that in the controlled failure, the shear cracks decrease with size. However, there are significant spikes here due to the possible dynamic effects from a large amount of energy being stored and not to be able to be fully dissipated as the size limitation of the OSBIT. So another thing we have been doing is the third part, so OSBIT and the post-peak compression. So we wanted to also compare the class 2 behavior in OSBIT and the controlled post-peak UCS test. So to get an overview of the overall post-peak behavior under different stress conditions. So 2 lateral strain gauges were used, and similar like the LVT in OSBIT, they provide feedback into the loading system mechanism. And here we use 3D DIC compared to 2D in the OSBIT, which also allows us to analyze both in 3D and in 2D. And as you can see, this is the comparison between the conventional and the controlled one, where we're eliminating this violent failure in the conventional compression tests, and we're controlling the post-peak behavior. And post-tests, they remain relatively intact. So 6 rock types were selected for this test, covering all sedimentary, metamorphic, and igneous rocks. And we started these tests towards the end of last year. Here are the results for post-peak compression. So the 3 strongest rocks, and then when they are normalized in the maximum load and displacement, they show significant or extreme class 2, while others show somewhat slightly class 2 or mixed class 1 and class 2 responses, which is strongly correlated to the strength and stiffness. So this is for the OSBIT. We can also see the extreme class 2 and then the slight or mixed ones. And one thing to notice here when you compare these two is the sharper snapback intention, which means greater energy dissipation. So these are the individual normalized comparisons. So starting off from the weaker rocks, here I'm presenting the strain evolution of the OSBIT and post-peak compressions in DIC contours. So under compression, it's a mixture of class 1 and 2, but intention in the OSBIT is more evident of a class 2 behavior. So this is for the limestone and then the Gosford sandstone. Next one is the Iranian granite and then the bluestone. As you can see for the bluestone, because we're starting to get extreme class 2 behavior, the snapback is at a similar degree. But they're all relatively controlled. Even if we have major cracks here, the specimen remain relatively intact up to the test. And finally, for the strongest rock, here more evident of the snapback nature. For calcaire granite, there was no clear failure axial cracks or shear planes, as it experienced this kind of brittle spalling, but it remained relatively intact until the end of the test. And for these kind of tests, for the brittle rocks, for the high strength one, they last up to 20 hours. So we run them overnight and leave them running in the lab and get the results the next morning. So here the Adelaide granite was not fully controlled because it failed at this point, but still the snapback was acquired. And this was the latest photo based on the DIC before it fractured. There's a large axial crack form, which was also managed to be captured by the 2D DIC. So to compare the post-peak responses in OSBIT and post-peak UCS tests, we used 2 brittleness indices, K1 and K2 by Tarasov and Potvin, which was used to analyze rock burst potential. In general, based on the values, the slopes of the snapback under compression was closer to absolute brittleness here compared to the OSBIT snapback. However, when taking in, for example, here the Gosford sandstone, the snapback is much more sharper with a direct turning point. So this means that the portion of energy dissipated compared to the total energy involved in the process is greater in Osbit. So plotting one of the brittleness indices, K1 here, there were also strong correlations with not only the peak strength, but also with physical properties such as density, porosity, and P-wave velocity. So the next step now is to look into the acoustics and the IC data for more insight into the overall post-peak behavior. So finally, the summary and moving forward, how we link the multi-scale. So in linking the multi-scale fracture behavior, as I have explained first, the micro to macro behavior was analyzed by correlating DIC strains, acoustics, and SEM observations, comparing the fracture behavior in Osbit and Brazilian tests. On a macro scale level, the size effect and cracking mechanisms was investigated, as well as the overall overview of the post-peak behavior in compression and tension. And currently, some upscaling numerical work is also planned to see the link between macro scale class 2 and how it affects the fracturing and fragmentation of large blocks incorporating joint sets or DFNs, which will be encountered in caving projects. And further expanding these scales, we are actually currently starting soon some nano indentation tests. So to connect the nanoscale properties such as hardness or elastic modulus of mineral grains, individual mineral grains, and how this is reflected into the macroscale class 2 behavior. So finally, I would like to acknowledge the support and guidance of my supervisors, Associate Professors Murat Karakus, Shell Professor Jiang Nguyen, and Professor Habui, and as well as the support from the Australian Research Council and BHP as part of this IRC linkage project, which is funding this specific project. So thank you. That is the end of my presentation.
All right, thank you. Yeah, thank you, Fauzan, for your excellent presentation. Basically, you've did a lot of, basically you've done extensive experiments by trying to capture the class 2 fractures behaviors, and also use several control facilities in Adelaide to capture the real behaviors of the rock. And so now I think the floor is open to the audience. Anyone has any questions to Fauzan? Any questions from the audience?
Mr. Fauzan, right? This is Yingchun. Yeah, very expressive laboratory work. And yeah, I have a very small question because I didn't do much work into the tension behavior. So my question is, so with your class 2 finding, with your findings on the class 2 behavior on tension, so how can we use it in the blockade project, or is there any implications for the blockading or disaster control?
Thank you for the question. So yeah, that's a very nice question. So what I believe the application will be on the rock mass scale, but we have to be careful here that because these class 2 behaviors, they tend to exist when we are testing on intact rock, which is free from defects. So when we are testing into the large scale, we incorporate joint sets, DFNs, then rather than failing through the intact rock, they will fail through the planes of weaknesses. But we also believe that in recent studies about deep underground excavations, with large confinements, then these joints, the weakness of these joints are restricted, and then the failure will still occur not only through the joints but also the intact material. So that's one thing that we hope to be numerically represented later. But another thing is the main aim of this research, like if we have limited data from the field, we get a few cores, we do some testing, we do post-peak tests, we know the energy density, and then we know your minerals, we know our mineral composition, we know our nano-indentation and physical properties. We think that by understanding the capacity of energy to be stored by the rock and the amount that to be dissipated. That could explain the whole feature of the rock mass. And not only for fragmentation, but by understanding how different failure, whether in confined, control, or uncontrolled tests, it could also affect, for example, hydraulic fracturing, ground support requirement, and also like rock burst seismicity risk.
Okay.
So probably that it's going to be a wide range of application.
Okay, so understood. So another very quick question. So you have done the size effect, right? Size in the laboratory. How about the shape effect? Since the rocks are in different shapes, maybe cubic, maybe in polygon. I'm not sure. Maybe did you consider the shape effect on the Steinbeck behavior? Is there any difference? No, I'm not sure.
We haven't really considered that, but that might be a good idea for the next project. But as far as I know, in our own research project, even though we're testing, this OSBIT has been applied not only for natural rocks, but also for 3D printed materials, cement grouted materials. So we expect to get, by applying this method, we get new characteristics of materials under tension, which has not been much discussed in our existing knowledge. I would say
okay,
that.
Thank you. Very fabulous.
Thank you.
Okay, thank you.
Thank you, Dr. Lee, for your questions. And we have Hansen putting his hands up. So Hansen, please go ahead with the question.
Okay, thank you very much, Mr. Fauzan. That's a quite good research. I have interesting question about the mineralogical conclusion, because in the brittle rocks, you test in several rocks. I want to know about your conclusion. Is there any mineralogy condition during test? You have several thin section in the granite, and then several blue stone and limestone. Maybe do you have any conclusion with mineralogy condition and characteristic? Because in your set, I saw that in the limestone you have high displacement rather than others. Is that right? Because
Yes.
this is quite interesting, because in limestone, in geology, in the advanced diagenesis, there are secondary fracturing in the mineralogical scale. I think this a bit a good interesting thing in mineralogy. Do you have any conclusion in mineralogical approach? Yes.
Thank you, Mr. Hassan, for the question. So for mineralogy, for thin section, we only have two at the moment, which is these gothosanton and granite. So this was just to look into the mineralogy side of things. But when concerning the individual strength of minerals and grains, different sizes, different grain boundaries, that is our next work, because we as I shown you here, we just prepared these nano-indentation samples, and they are lined up for some test. Probably for mineralogy, we don't have any conclusion at the moment, except for this, the overall porosity. So porosity, density, and then the ultrasonic velocity, which reflects the structure, but not for specific compositions of rocks. So this is the general, okay, there's a good trend with porosity, density, and then ultrasonic velocity, but how is that reflected by the mineralogy? We need to wait for the nano indentation results. Probably that would provide a much better link with the mineralogy side and then to the microscale behavior. But yeah, I consider that a very useful input. So thank you for the comment.
Okay, can you show the slide on the displacement
Oh,
on the
this one?
Yeah.
Yes, yes.
As you can see, we have a low load, but we have high displacement on limestone. Yeah, because I think that's a quite interesting thing when we try to approaching with the mineralogical. Yeah, maybe that's it's quite good trend.
Yes.
In my opinion. Okay, thank you.
Because, yeah,
So,
the sandstone itself is very porous, so I think it has 32%. So it might affect one specimen to another. The amount of displacement can vary a lot because of the high porosity. I think that would be the one of the reasons, I believe.
yes, as we can know, as we can see that limestone has the secondary porosity that it can affect that secondary from the fracture.
Yes.
Okay.
Right.
Yes,
Thank you,
thank
Mr.
you.
Hassan.
Thank you, Mr. Fauzan.
Okay, thank you. Thank you, Hassan, for your questions. And anyone else having questions? All right. So if nobody has any questions, I think that's pretty much everything from Fauzan. And thank you, Fauzan, again for your excellent presentation. Yeah, I'm pretty sure audience did learn something from your presentation. All
Thank
right,
you,
so,
Doctor. Thank you.
Thank you. And now let's move on to the very last speaker of today's seminar, Dr. Yuqi Song. And he described himself as a passionate interdisciplinary research fellow. And the reason why this is the case is because he did his PhD in geomechanics with Professor Ranjit and Dr. Bailin Wu from Monash University. But at the moment, what he's interested in is how to apply computer vision techniques and impact mechanics experiments for the smart car, right? How to detect the obstacle in front of the car. I think that's these two research apparently are quite distinct to each other. That's why I would say, yeah, it's true that Dr. Song is a very passionate interdisciplinary researcher. And today, Dr. Song is going to deliver a presentation on the granular materials dynamics and bio-consolidation, right? So now let's welcome Dr. Song, and time is yours, Dr. Song. Please go ahead.
Yeah, thanks for the introduction from Dr. Dang Li, and also thanks for my nominee is Dr. Babak, who invited me to join this seminar. Yes, so I'm sharing my screen. Yeah. Yeah, so also thanks for International Society of Rock Mechanics and Rock Engineering for hosting this event. And I'm Dr. Yuqi Song, working as a research fellow at the Deep Earth Energy Research Lab at Monash University, and supervised by Professor Ranjit and Dr. Bailin Wu during my PhD and postdoctoral stage. And today's presentation is quite reflect the research concerned with rock mechanics, but not automatic driving cars. That's one of maybe my future interest. And my topic is the granular materials dynamics and bioconsolidation. And here is the outline of my research. The first one is I introduced CFD-DEM and some experimental study on the granular dynamics. So my granular materials here is including like the sand in a petroleum and natural gas hydrate reservoir, like the microplastic as emerging pollution, and also some rice. Rice is a very interesting. It's a non-spherical particle. Yeah. And topic 2 is the bioconsolidation of particles by the microbial-induced calcite precipitation or the enzyme-induced calcite precipitation. So it's a it's my research during my postdoc stage and cooperate my friend and the connections in chemical engineering. Yeah. And a new research topic is some new thinkings on the STEAM education. Yeah. And firstly, let's start from the my bio. Yes, I have introduced that I'm research fellow, and my research contribute to the United Nations Sustainable Development Goals. And topic 1. So firstly, my scenario will be put it in the sand production in the petroleum engineering or natural gas hydrate engineering. So what is sand production? So sand production means the when we are developing an oil and gas, so the oil or water or the natural gas flow that carry the sand particle flow from the reservoir into the perforation and finally into the well bowl. So we want to develop more natural gas, more petroleum, but we don't like the sand production because the sand production may choke the well, may damage the safety wall, may damage the pipeline. Yeah. So actually, the sand production is a erosion phenomenon. So also similar to the piping in a dam, or so similar to the water inrush when we are doing a tunnel. Yeah. And sand production is becoming a more and more serious problem all around the world, especially when a underground hydrogen storage. So we need several round of the times of the injecting the hydrogen into the reservoir and to extract it outside, so or it damage the reservoir. So firstly, let's look at our self-developed, the transparent, visualized sand production cell. So this sand production cell is featured by a transparent screen, and when we are doing experiment, we just fill this square area with the sand particle to simulate the reservoir, simulate the strata. And we inject the fluid, like the water or petroleum, natural gas, or gas from the top of the cell, and it's a flow out from the outlet located at the central bottom of the cell. And for the outlet, we can simply plug in the sand control. As I mentioned, we don't like sand production, so we can plug in sand control equipment. Is a equipment with an open of 1 millimeter, 3 millimeter, or 5 millimeter because it's a plug-in equipment. It's a plug-in outlet, so it's easy to switch from different millimeters. Yeah. So its usage is to simulate the slot liner or simulate a wire-wrapped screen or standalone screen to manage the sand production. And for the left figure, we can see that there is a shelf to exert the actual load on the reservoir, yes, if necessary. And according to the experimental equipment, I developed this 3D true tri-true, the CFDD numerical model to simulate the sand production. And similar to the experimental model, we flow the fluid from the top boundary, and it's a flow out from the outlet located at the central bottom of the cell. And if necessary, we can just apply the true tri-true load on this model filled with sand. And let's look at some results. So as we know, the DEM has a feature to capture the microscopic phenomenon of the reservoir of the sand particle contact with each other or the force chain. So for the force chain here, we can see that when we're increasing the fluid pressure from 50 kilopascal to 75 to finally is 2100, we can see that the whole reservoir, the whole sand assembly become denser. And at the beginning, there's some unconnected force chain here. But gradually, when the pressure is higher, so there's no unconnected force chain. And another interesting thing is that we can see that a sand arch located at a central bottom. So like it spans over the open, so it spans over the screen. And its color is red because its contact force is higher than the other parts of the reservoir. So that means that the sand arch bear most of the force that transfer from the reservoir to the sand arch. So the sand arch is like an arch in the architecture or in a bridge. So as we know, sand is a material that has no tensile strength. So just like concrete, so concrete is a material, it has a much higher compressive strength than its tensile strength. So sand is similar to the concrete, and it has no the tensile strength. So arch is a very ideal it's a shape for this kind of material. And the sand arch, the stability of the sand arch is related to the well control of the sand production. So when a sand arch is collapsed due to the high drawdown pressure, so we want to develop the oil and gas, the natural gas faster. So we usually increase the drawdown pressure and increase the velocity, the fluid velocity of the fluid. So a sand arch may collapse. So it's very important to do research on investigate the sand arch, the shape and its spanning over the and the stability of sand arch. Yeah, and this is a very intact sand arch when we are deleting the reservoir above the sand arch. Yeah, from this figure we delete the reservoir formation above the sand arch, and we can see the intact sand arch shape. And force chains here. And if we investigate the particle size distribution of the reservoir and the sand arch separately, we can see that the sand arch is formed by the sand particle that is a bit larger than the reservoir. That means the greater particles are easier to make an arch over the over the outlet. And another interesting thing is that the sand arch shape is usually in common sense it's locally convex, right? But in our sand arch, so we found that the concave sand arch, that is the theta is larger than 180 degree. So we see that a particle comes from above the equator with the angle is larger than 180. The theta is larger than 180. So for this condition, we conclude that when the frictional force is taken into consideration, can we see this phenomenon? And it's it might be unstable, right? So it's instability can be compensated by its neighboring particles. So as I mentioned, so it's very important to know the collapse and the reconstructed of a sand arch. So here I have captured a reconstructed process of a sand arch at a simulation going to the 86.0 second to 86.02 seconds. So this reconstruction process lasts only for 0.02 seconds, a very short time. And when I increase the drawdown pressure from 1300 to 1400, I see this phenomenon. So the particle B is kicked, or we can say it's flushed away by the fluid, and its place is replaced by the particle A. So in left figure, we can see that CBD is formed previous sand arch, and this sand arch is collapsed, and the new sand arch formed by the particle of CAD. And also I investigated the influence of in-situ stress on sand production. So when I increased the vertical stress from 1 megapascal to 20 megapascals, so we firstly see that the porosity of the porosity distribution of the reservoir become is lower when we are increasing the vertical stress. And following by the porosity is becoming lower, so we can see that fluid velocity become lower either. Yeah. So we can say that a high vertical stress resulting in low porosity and finally reduce the fluid velocity. And lower fluid velocity just to have the lower drag force act on a particle. So we can see that here is a larger area have a drag force like this, but in the right figure, so it's a smaller area. And yes, so there are two reasons. Drag force, so higher vertical stress resulting in low porosity and reduced fluid velocity. And high vertical stress result high maximum static frictional force, and it makes the shear strength of the porous media higher, so to overcome the drag force. And for previous study, I investigated uniform reservoir, uniform strata, but in real cases, some strata might be the well-graded or gap-graded. Yeah, so here I investigate the construction process of the sand arch in a gap-graded reservoir. So we can see that there are three steps of the sand formation. So at the beginning of the simulation, so the coarse and fine particles are producing together. Yeah, we can see that the coarse particle and some blue particles are the fine particles. And in stage 2, so we call the migration stage. So we can see that a sand arch consists of the coarse particle has been formed, and the fine particles still migrating across the sand arch. So the coarse particle nearly stopped moving in this stage, but the fine particle is still moving, as shown by the arrow. And stage 3 is the equivalent stage. So when the fine particles stop moving, so we know that the sand production is stopped and controlled. Yeah. And some typical particle bridge about the coarse particles. So one particle can migrate across the throat, the void formed by the coarse particle. And its mathematical calculation is as shown in the right figure. But three particles meet together at the throat. So we can see that it's choked here. Yeah. And we also investigate the different, we change the particle size of the fine particles here, but we keep the 90% of the coarse particle the same. And we can see some conclusion that the first one is the reduction of the size of the fine. So the percentage of fine particles is producing more than the coarse, yes, the percentage is higher. Yeah. So we can see that is for the coarse particle, so there's nearly no particle migration, but for the fine, it's 75 to 212, there's a great particle migration is observed here. And the strata with smaller fine particles produce more sand. And we also investigated the stability of the reservoir by a newly developed software called Ciscus, and matched with the experimental and numerical simulation well. And I also investigated non-spherical particle, the rice particle, because rice is a very easy obtained particle. That's typical non-spherical particle. And we can see that for the rice particle, for the ellipsoidal particle that has the same volume with the spherical particle, it has more than 11.8 times this choking choke strength than the spherical particle. Yeah. So also the ellipsoidal particle has different orientation. So just like the spherical particle. So when we are changing the orientation of ellipsoidal particle, we can see that for the left cases, the particle is aligned in this direction, and right cases is in the direction that perpendicular to the outlet plane, and we can conclude that the left figure is the most easy case for the ellipsoidal particle to go across the outlet, but the right figure is the most difficult case, and the difference is 1.9 times the particle choke strength. Yes, and there so some it's when a particle is flowing, so the ellipsoidal particle is just turning to its flowing direction. That is one phenomenon. And do you still have time? Yeah. Yes, so next I investigated the particle movement in the shear band. So shear band is anywhere, and my method is using a function called a sigmoid function to characterize the particle movement in a shear band. And we firstly just turn the common the y and x axis to the ij axis, and ij axis is I is perpendicular to the shear band, and j is along the shear band, and we can see that things become easier. And we can see that particle displacement when we are using the ij, the axis is like this, and we fit it by a function called a sigmoid function. And to increase the accuracy of the curve fitting, we cut the shear band into 7 pieces. Like yeah, it's in this direction. We cut into 7 pieces, and we do the curve fitting is for each pieces separately, and we finally put them together. And this is the sigmoid function, and actually it has we have given some physical meaning for each parameters. It's not only a curve fitting, but it has real physical meanings. So we can see that the left figure is the DEM result, and right hand is a sigmoid function result, and it yes, matches well. And let's look at some bio-consolidation. So we use the emerging technology called the MICP to control the sand flow to increase the sand slope stability or to stop the migration of the microplastic pollution. And firstly, we optimize our the fermentation medium. And we use the alkaline treated fiber. As we know, the MICP is generating the calcite. So calcite is a mineral that is a rock-like mineral. It's a rock mineral, and it has a higher compressive strength than its tensile strength. So when we are doing UCS, so if we add some the treated fiber into the sample, we can see that the UCS strength is increasing, and the jute fiber is here, yes, under the SEM. And in the future, we want to apply this technology on the space construction. And also, it can be used to control the migration of the microplastic pollution. And finally, let's look at my proposal for the STEAM education reform. So cooperate with Ms. Shuya Yan at the University of Queensland. So for long term, I have the following 3 questions. So the students are gaining knowledge via online videos. So what's the purpose of our universities? And secondly, so when AI surpasses humans, so what is remain unique for our human? And are we educating students to compete with AI or to collaborate with AI? And So our key philosophy is to empower students to collaborate with AI, not compete. And we believe students who can't master AI tools will struggle to find jobs in the AI era. And beyond merely integrating AI into education, so there has been many studies in integrating AI to improve the education quality, but we focus on the fundamentally redefined learning content. And our key methodology is firstly using the problem-based learning. So put students in the real cases, the real problem, and they can gain the knowledge via doing the project. Yeah. So it's different from the traditional knowledge-based learning. We believe that students don't need to know this knowledge before they get in the problem. So yeah. And secondly, we actively encourage and equip our students to leverage AI tools for effective problem solving. Yeah, so it's we are quite radical here. So we encourage students to using AI. We prefer they using AI. And finally, we use some technique like question formulation technique to train a student when they are facing to a blank chat box with the ChatGPT or the generative AI. They need to raise very high quality questions, and in that way, the ChatGPT can reply them with some high quality answers. So high quality questions lead to the high quality answers. So we need to improve students' ability to raise questions. So that's our key methodology. Yeah. Yeah. So thanks for listening and thanks for organizing this event. Yes.
Okay. All right. Thank you, Dr. Song, for your impressive presentations. As you can see, like Dr. Song has a very broad research area. It can be from like a conventional geomaterial, geomechanics research to education philosophy research. And now the floor is open. The floor is open to the audience to ask questions to Dr. Song. Any questions from the audience?
So I can talk a bit more to wait for more questions. As I added a slide, it's not containing my presentation, but I think it's Professor Lee from the Dalian University, the Yingchun. Are you still here? So you may be interested in this figure, in this research, as I mentioned, is using DEM to investigate a rock sample with a rough fracture. Yeah. Yeah. It's also open for question. Yeah.
So does anyone have any questions to the content Dr. Song has covered so far? If no, I have a questions, Dr. Song. So you've done extensive numerical simulations with the PFC, and you've also done like you've also have your lab scale experiment, right? Trying to simulate the sand production. So my understanding is you are trying to understand the sand production or the porous materials, how the water would flow, how the sand would be produced through the porous materials, and also by understanding better that the behavior, you have a better design of the sand slope to make it more stable. Is that what you're trying to do? And so
so you go.
Yeah, it's quite fundamental. Yeah, I know. And for PFC, so I have no expertise in this PFC, but my understanding is the PFC has a lot more parameters, input parameters than DEM and FEM, right? Like I'm not sure if it's correct, like a shear stiffness or normal stiffness between the particles. Like how did you calibrate those parameters and how to validate the model? So that's something like I would be very interested in. Yeah.
Yes, thanks for very good questions. Yes, two questions. First one is so my study is I try to control the flow of sand. You know that sand is not flowing in the reservoir when we are developing the natural gas, but also is flowing when it's in a desert, right? In a sand slope control, we need to increase its stability. So if we know the fluid coupled with solid, so how's the fluid is flushing away the sand particles, so we can increase the stability of each of them in each cases. So that is yes, is really my purpose. Yes, and yes, as you mentioned, most of my studies focus on the sand production. That's sand flow in the reservoir. But in the future, these mechanism can be applied to the in a slope or even in the, as I mentioned, there's a new emerging pollution called a microplastic. Microplastic is also a particle, and we wanna. There's not very good the method to control it, right? So it's but it generates usually in a landfill. There's a rubbish landfill, or it's like agriculture, the membrane, yeah. So generate a lot of microplastic pollution, and we can control it once we know the particle fluid is interaction. Yeah, that's for your first question. And for second one, so it's a good question. It's, I didn't show the parameters here because of time limitation, but it's yes, it's include a lot of parameters, more than 20 or 30 parameters, and I used generally there are two calibration methods. First one is called a bulk calibration, and second one is called a microscopic calibration. The difference is that bulk calibration means that we do macroscopic test, like what we are doing in our experiment, and we do the similar testing in the numerical simulation, and we compare the result output from the experiment and the in numerical simulation, the DEM, and we adjust the input parameters of DEM, and once we get similar the output, the similar phenomenon, and we can say that it has been calibrated. Yeah, so usually we use this kind of calibration. But there is a new calibration method called the microscopic that we do the microscopic experiment, just like we want to know the frictional. Yeah, the friction of the two particles when it's in contact with each other. What's the friction between the two particles? Yeah, so we can do very microscopic test to identify the friction. And another is like a capillary force. So what's the capillary force between two sand particles? So how large it is? So there is also a microscopic experiment. We can investigate the capillary, the liquid bridge force between the two particles. It's quite micro because usually the sand particle is only 1 millimeter, and it's we need to do the test in that level. So it's a microscopic level of the experimenter to calibrate the DEM. Yeah, there's usually two-way, and two ways are both acceptable. Yeah, that's my answer. Yeah.
Okay, thank you, Dr. Sung, for your answers and response. And anyone else have any questions before we wrap it up? So now, if nobody has any questions, I think that's pretty much the end of today's seminar. So what do we do? I'll hand over to Yudi, and for your
All right.
to close up this seminar.
Thank you, Dr. Lee. Yeah, that's pretty much it. As we conclude the 16th ISRM Young Members Seminar, on behalf of organizing committee, myself, Dr. Babak, Dr. Dan Kili, I would like to express the gratitude to the ISRM for their support in organizing this committee. And also for the audience, thank you very much for your attention, and special thanks to our speakers here. Once again, Dr. Yingchun Lee, Mr. Fauzan, soon to be doctor, I believe, Mr. Fauzan Yudho Pratomo, and Dr. Yuqi Song for their valuable presentation. I hope this platform can benefit you in terms of new perspective, fresh insights, and also future challenge for your research. Okay, for the upcoming updates, we will update the information in the isrm.net, the website of the ISRM. And also, if you are a member of ISRM, you will get the ISRM newsletter, and you can find the information there about our activity. Okay, thank you all for the participation. Have a good day. Bye-bye.
Bye-bye.
Thank
Thank
you,
you.
Dan.
Thank you, everyone.
Thank you,
and
everyone.
Have a nice
Bye.
Have a good night.
Bye.
Bye-bye.